Okay. Okay, so let's begin. Right? We've wasted like 5 precious minutes. So welcome to week 6, and thank you for everybody who's attending this class today, even though this is Chuseok, the holiday seasons. So hopefully we can. There's not a lot to be covered, specifically talking about GAN only, but there are some other stuff that is kind of interesting. So hopefully we can wrap this up in 1.5 hours. So we will talk about these obviously we're going to talk again, and then there is this interesting comparison between VAE, this is what we learned last week, and then GAN, and something called autoregressive model, which everybody should be familiar with these days, especially with the GPT and LLMs, so autoregressive model. And then slightly we're gonna cover like diffusion, because we're going to learn diffusion anyway, so we're going to only touch upon how diffusion compares against all these three, and then how to evaluate GAN or any generative model for that matter, anything that generates an image. It could be VA, it could be autoregressive, could be GAN, anything that is any generative model that generates image. We need to evaluate how good the quality of the image is. So that's what we're going to talk about, and then some applications of GAN. Right, so generative adversarial. So VAE recap. So VAE was just an autoencoder plus a regularization term. So autoencoder with an encoder, encoding phase, and the decoding phase, compression, decompression. And then there's the code or the latent variable or latent representation, all the same. And we want this latent space to be to follow a certain distribution, certain shape, and that shape happens to be PZ, which is usually Gaussian. N0i. So this KL term, this KL regularization term, is that while compressing and decompressing an input to the output, we want the latent space to look like a Gaussian distribution, a standard Gaussian distribution. All right, I'm going to have to mute everybody. Okay. So that is it. And this allows us, so VAE recap, so we are approximating, we talked about the loss perspective, which is simply just a reconstruction term plus the KL term. So the reconstruction term being the original objective function and the KL term being the regularization function. But we also talked about the probabilistic perspective, which is that all that VAE does, after you go through the equations and you derive the equations and all that. After you do that, you realize that what VAE actually is doing is we are trying to maximize the elbow in the posterior in the variational inference, or people call it variational inference, variational Bayesian inference, variational Bayes, whichever. Anyway, we're trying to maximize the elbow. So that was our understanding, and that was the beauty of VAE. It's both. It makes perfect sense, right? So what we're trying to do is we are trying to mimic the true PZ given x. PZ given x is the posterior distribution, right? So we were trying to approximate PZ given x with a known function QZ given x, which, so that was a variational inference. But by sampling from this QZ, which we can convert that from convert to the x. So we don't know the true PZ given x. So the true PZ given x could look like this. And since we're approximating with a normal distribution, the best we can do is probably this, right? Or actually, so there was an interesting question from last week who asked, I forgot the name of the student, but the question was, what happens? Why use KL? Why use DKL QP in variational inference instead of DKL PQ, right? PQ. So I think that was the question. And my answer was that this leads to the standard variational Bayes, and this leads to expectation propagation. And this we usually go for this one instead of this one. That was my answer. But after looking at this, I actually realized that there was a significant difference between the two. Difference between this guy and this guy. So you see here that if you go this route, you will get this. Not exactly this though. You will kind of look. It'll kind of go like this, or more precisely, if it's maybe like this, So I forgot the so what the first one does is that the first one penalizes when the Q function, which is the approximating, which is the one that approximates, and P is the target, right? So the P doesn't change. It's the Q that changes, right? So P is an unknown function, unknown distribution that we don't know, and it doesn't change. It's a ground truth, but we don't know. And Q is the one with a parameter. So we are trying to tune the parameter so that Q and P becomes as similar as possible. But there are two ways to do it. There's QP and PQ, right? So QP is this was this is QP and this is PQ, right? Oops, right. So these two are not the same. They're not the same. So KL divergence is not commutative. They're not this guy and this guy, not the same. But you see here that if you go to this route, if you go to this route, the bottom row, then it means that then if you see here that let's see, what was it? So if P is non-zero, if P is non-zero, if P is like non-zero, there's a support. And if Q is zero, so let me write it down. This guy, when P is non-zero and Q is zero, what happens? What happens is that this guy will blow up. The log term will blow up because P is non-zero and Q is like almost zero. Then this guy will blow up. That means that log is a monotonic function. So this guy will blow up. And that means that your DKL will blow up, right? So that means that whenever P is not zero, Q also has to be not zero. So this is not good. So whenever P is not zero, Q must also be not zero in order to minimize this guy. So that means that it is trying to cover all the support. So Q is trying to cover all the support of P. Whenever there's P, Q must be there too in order to minimize DKL PQ. So when you use DKL PQ so that you want to approximate P with a Q, then you will end up with a Q that looks like this. Like this. Maybe with a with a red line. Like this. Right? So as long as there's ever slight P's here and here, Q will also have to be there. So that's the behavior of this guy. But with this guy, with the QP, it's the other way around. So whenever there's Q and there's no P, so whenever there's Q but no P, then that will blow up the log term. So you don't want that to happen. So in order for this guy to go down, in order for the DKL QP to go down, Q must not be there whenever P is not there. So that is why we will see a line like this. Kind of like this. So because if it behaves like this, like if there's a gap between the two, then using QP, if there's a gap between the two, like Q is higher than P, that means this guy will blow up. So we don't want that to happen, right? So that is the difference between the two. So PQ, so this diagram is a little bit like it's neither this or this. So the actual PQ will look like this guy, and QP will look like this guy. Right? So obviously it's up to you to decide which one you want to use, right? Obviously, I mean, if you use PQ, then it'll try to cover all support of P, and that will lead to inevitably, if your true P is bimodal or multimodal, like for that matter, like this, then it'll inevitably lead to a big gap, such as this one, There's a big gap between the two, but it will try to cover all support, so it won't miss it. It'll have a high recall basically. But QP will only cover one mode, one specific mode. So at least if you use this, then Q will produce only the likely like samples that only likely according to like the P distribution, but it'll never cover this guy. Like if your Q is like this, then it'll never be able to sample from this region ever. So the recall will be low, but the precision will be high. Right? So hopefully this makes sense. And variational Bayes, again, like variational Bayes, I've looked up the internet to search why variational Bayes goes this route. I don't think I've found a good answer, but it's just what it is. But at least we know the behavior between the two. Does that make sense? All right. Okay. Hopefully. Okay. All right. I'm gonna move on then. Anyway, so that was VA, and then we have another model family called autoregressive models. So the first autoregressive model was in terms of image generation, I think it was Pixel CNN or Pixel RNN. There were like two papers, Pixel RNN and Pixel CNN, and then there was like Pixel CNN Plus, and then there were some papers from the researchers of DeepMind back in 2015, 16, I think, and it was basically what I just said. Generate images 1 pixel at a time. So if this is like what is this? This is a 7x7 image, 7x7 image. Then you start from the first pixel, and then you generate the first pixel based on the second. You first generate the first pixel, generate the second pixel based on the first pixel, and then generate the third pixel based on these two. Generate the fourth pixel based on these three, such and such. So you just keep generating next pixel, just like you generate next word in ChatGPT. So obviously it'll take a long time because typically images are like, I mean, MNIST is like 28 by 28, so it's doable. But if you think about like 128 by 128, then that's what? That's like 40,000. Oh, sorry, no, that's 20,000. Yeah, wait, 128 is 2 to the 2 to the 7, 2 to the 7, so it's 14, so 2 to the 4, 16,000. Okay, so it's 16,000. So 128 by 128 is 16,000 pixels. So you have to do a for loop over 16,000 pixels. So that will take a long time, right? Even now, GPT-4 is like 16,000. It has a 16,000 token span back then. So you can't like generate 120 image with a pixel CNN. And then, so that's another issue. So, and then there's something called WaveNet, which is generating audio 1 frame at a time. So if you think about what audio sample rates are, such as like 256K, 128K, if you listen to MP3, then it'll typically like 128K, 196K, 192K, 256K. So that's again, a not very, very, very high sampling rate. So you will have to do like a for loop like for a very, very long time. If I remember correctly, generating like a 4-second audio file with a WaveNet took like hours. So unrealistic again. And then there's like GPT-3 and DALL-E 1. So if you remember DALL-E 2, I mean DALL-E 3 was released like maybe a couple days ago or several days ago. So DALL-E 3 and DALL-E 2 are a diffusion-based model, but DALL-E 1 was an autoregressive model. So, but it didn't generate 1 pixel at a time. It generates something called 1 visual code at a time, but maybe we'll have a chance to talk about this later. Right, so those are the autoregressive models, and the gist is that they are all following this formula here. So your joint distribution, so your x is like an image or some sample. So your sample's joint distribution meaning like all pixels in your image. They can be modeled with joint distribution, right? Can be broken or can be factorized into this form. So if you remember like a basic probability theory, your P X, well, let me just write it down. A, B, C can be broken down into P C given A, C given B, C time if C given B A times P B given A times P given A, right? So you can factorize it like this. So that's what's happening here. So you start with the first pixel, then you generate the second pixel based on the first pixel, then you generate the third pixel based on the first 2 pixels, and so on and so forth. All right, so it works very well, but slow in inference. And then there's another generative model family, which is that, so these two, the VAE, we actually are mathematically approximating the true the model the sample the true sample distribution. Like where does the image come from? Like there's like you can imagine an image having a like a distribution in a latent space. Like if you think about your image is 128 by 128 by 3, it has a 128 by 128 by 3 dimensionality or resolution, then you can think of a space where all samples from this where like how large is this? 16,000 times 3, so it's 48,000. So it's 48,000 dimensional space where all samples are just scattered around. All samples are scattered around, and some are dogs, some are cats, some are humans, and some are just complete black, complete white noise or like blurry things. So you can think of the like a space looks that is filled with like a lot of image samples, and obviously some images will have a high density, like all dog images. Like all dog images can be here, like husky, chihuahua, like golden retrievers, like border collie, whatever. And then there will be like people here, and then there will be cats here, like this. So the distribution would be like there will be high distribution here and here and here, but most of the space, most regions in 48,000 dimensions will be completely just zero. Will have zero support because nothing like complete black, complete white is not realistic images, right? Or even like noise, like Gaussian noise is not a realistic image. So there's a certain distribution that we can imagine, and what these VAE and autoregressive model is trying to do is to approximate that space, that the density with a certain like a parameter. Like so with this we are assuming that we can compute the joint distribution with factorization. With VAE, we're assuming that we can approximate the latent distribution with QZ given X, so that we're actively trying to estimate it with a parametric function. But here in this family, this generative model family, which is which the GAN is a member of, we don't care about the data distribution. We don't care. We don't want to actively seek after the mathematical model, like parametric model or parametric function that approximates the density of these images. We just want to generate good synthetic samples, and that's it. So we no longer care about the underlying distribution. We just want to sample it. We just want to get as real images as possible, and that's all we care about. So that's where GAN comes in. So typically what GAN achieves is that we sample a random noise from some random distribution. Could be uniform distribution, could be normal distribution, doesn't really matter, but people typically use either of those two. So it's either normal or uniform. So some random distribution that we can sample, we can like get samples from, and then we put it through something called generator, and then we get an image, and that's it. And we don't know how likely that is. We cannot calculate the likelihood of this image, but we can with this. Like we can put all the pixels into this function, and then we can calculate the likelihood. Or with this, we can also calculate the likelihood, right? But here we cannot calculate the likelihood. All it does is receive a random noise and then convert that to a real image, and that's all it does. There is no probability or whatsoever. So that's the whole point about GAN. There's something called diffusion, so which is also, it doesn't care about data distribution. So it's kind of, you can think of diffusion, which we will learn in several weeks from now, which we will learn. You can think of this as like a chain of VAE or multi-step VAE, because we do like a we like slowly remove the noise. So we will start from the complete noise, and then bit of a denoising, another bit of denoising, another bit of denoising, another bit of denoising, all the way, and then you'll start to see like some shape, like it's like semantic basically, and then you keep denoising until you get a very, very clean image like this. So there's a variational inference involved, Bayes rule variation inference, and representation. Like all this is involved. So if you have a good understanding of VAE, understanding diffusion won't be too much of a problem. Anyway, so again, like this guy also doesn't really care about the data distribution. And all it does is give us a really, really high quality image, just like GAN, right? But diffusion later, GAN first. So GAN, assuming a lot of people actually are familiar with GAN, so it's a two-person game, and there is a game. So game between two parties, and one party or one person is called generator. Another party is called discriminator. So it's a game between the two. It's a competition, and you can think of this as a game theory. So two-person is a game between you can apply game theory using these two players, and that is why GAN acquired like a lot of fame, because it has such a nice theory behind its formulation. So what G, the generator, tries to do is to fool D. D is the discriminator. So G is trying to fool D with fake samples. So G is the one that generates fake samples, and it wants to fool D. So what does D do then? D tries to discriminate between real and fake samples. So D is like a police, it's like a cop or a judge. It's like a referee that says which one is real and which one is fake images. So D is a cop, and G is like a perpetrator. It's like a criminal that or hacker that wants to fool D by creating as realistic X prime, the fake sample, as possible, so that D can no longer discriminate between real and fake, because the fake is so realistic, you can't distinguish between the two. So that's the whole setup between the two players, the G and D. So figurative, architecturally, it looks like this. So there's, again, the random noise Z, which comes from normal or uniform distribution. We'll just stick to normal distribution. So it has random noise from normal distribution, and you put that random noise. It could be, and again, this Z could be anything. It could be R128, R64, R8. Doesn't really matter. It's a hyperparameter. How large of dimensionality Z you want it to be, it's up to you. You can use like 32, 28, 128, doesn't, whatever. And then generator will be receiving that. Let's assume, let's stick to a concrete example. So Z comes from normal distribution, and it's a vector. It's a vector of dimensionality 32, for example. Then what generator does is generator receives a vector of 122, R32, and then converts it to, let's say, 128 by 128 by 3, like R128 by 128 by 3. So high level, like a medium resolution image. So that's all generator does. So there's no like probability or anything involved here. And then all the samples generated from the G will be X primes. They're the fake ones. And then there will be another pile of samples that are real, that are kept, they're taken from the real world. So these are all X's. So there's X prime and X's. And what discriminator D does is to just simply say which one's real and which one's fake. So, and it's an end-to-end training procedure. Right, so that's the setup, and then the two have so GAN is basically binary classification. So because what D does is basically is 1 or 0. 1 meaning it's real, 0 meaning fake. It's a binary classification. But these two players have different goals. For D first, it needs to successfully distinguish between the two, the X prime and X and X prime. So D needs to succeed the binary classification, but G needs to trick D, which means G wants the binary classification to fail. So they too have a competing objective. So G wants to fail and D wants to succeed. And that is where the competition begins. And then when these two reach a equilibrium, then the game, then the training is over, basically. We have a perfect situation where D and G reach an equilibrium, and we call that Nash equilibrium. If you're familiar with like game theory, I'm not, but in the original GAN paper, they prove that when G and D reach a Nash equilibrium, then we have a perfect generator. So that's the whole setup. So we'll start with since this is binary classification, we'll start with the cross entropy, obviously. So cross entropy, we all know that we can use it for binary classification. And the cross entropy objective function or loss function looks like this. I mean, this is not a loss function. Loss function, we need like minus here, but this is just cross entropy, right? So all the positive terms go here. All the positive samples go here. All the negative samples go here because positive samples will have yn equals 1. Yn equals, so let me just write it down here. Positive samples will have y equal 1. Negative samples will have y equal 0. I mean the true y, not the y hat. That's a prediction. The true y will be 1 for positive, and y will be y equal 0 for the negative. So if this is 0, so obviously for negative samples, this term goes away. For positive samples, this term goes away. So we're left with either only one of the two terms. Right. So as I said here, the positive sample, negative samples, and assuming that we can separate, assuming that there are same number of positive negatives in your training set, so 50-50, then we can separate positive samples and negative samples like this. So half of the training samples are positive, half of the training samples are negative. So we just break them down into two parts like this. And then some number manipulation. You put half out and then you turn this into n over 2. So nothing really, it's the same thing. Nothing changes, right? So nothing changes. And then what happens is this is a what? This is a mean. So it's an average, right? This is an average. So it's a mean. So you can think of this as like an expectation. This also is the same. So we can think of this as an expectation. So what is this an expectation of? What is this an expectation of? This is an expectation over the positive sample, and this is an expectation over negative samples. So far so good, right? So we're just step by step manipulating the good old cross entropy. So we separate between the positive and negative, and then we do some simple manipulation, and then we turn this into a mean. So you can, like, if you're familiar with the statistical theory, like sample mean, this is a sample mean, right? So sample mean is an unbiased estimator of population mean. So this is a population mean. So we're trying to estimate the population mean by using this trick. So with that, we lose this 1 over 2. So this half, because in the end, what we're trying to do with cross entropy is we obviously want to maximize cross entropy, right? So we just lose 1 over 2 here. We just lose it. So we're left with this. And then this guy, this positive negative, is now becoming real and fake, because when we're doing binary classification, we want the real samples to be 1 and fake samples to be 0. So positive is now turned into real and negative is turned into fake. So far so good, right? Nothing, there's no change at all. And then after that, we know that x prime is a fake sample generated by the generator. And what does the generator receive? It receives a random noise z. So what we did is x prime became gz. That is the only difference. Oh, and also, since x prime was a fake sample, now the only determining factor that generates a fake image is the z-pz. So pz being the normal distribution. So we sample z from a normal distribution, and then we plug that into the generator, and then the generator will give you x prime, the fake image. Right? So good. So far so good, right? And then the only thing that's left is, well, we need to parameterize the functions so we can learn something, right? So we parameterize the d function with theta d, and we parameterize the generator function g with theta g. And that's it. So this is our objective function. So we want to do something with this objective. We either want to maximize it, minimize it, something. We want to do something with this this objective function. So we're left with this. So for D, as I said, they had a conflicting goals. So for G, it needs to fail. For D, it needs to succeed. So going back here. For D, it needs to succeed the binary classification. So we want to maximize the cross entropy, right? So with theta D, which is the discriminator parameter, we want to manipulate the discriminator so as to maximize this cross entropy or succeed the binary classification. But for G, we want to fail it, so we want to minimize this cross entropy, and by manipulating the generator's parameter. But if you look at this term here, it has nothing to do with theta G, right? There's no theta G in this term, so we throw it out, and all we are left with is the second term. So D has this term to satisfy. I mean, for D, it needs to perform this, and for G, it needs to perform from this. So there's like a conflicting goal between the two. Right, so that's why we call GAN. If you've heard about the min-max game and whatnot, when you're reading GAN paper or when you're reading like GAN blog or something, GAN is a two-person min-max game because one guy wants to maximize this objective function, and another guy wants to minimize this objective function. So it's a min-max game between. So it's a competition between the two, right? So yeah, discriminator wants to maximize the objective such that dx is close to 1. Dx is close to 1 for real, then dgz is close to 0, which is fake. And generator theta g wants to minimize the objective such that dgz, this guy, dgz, close to 1, because dgz is when discriminator is receiving the fake samples, right? For we want to make this dgz close to 1, and that is what G wants to do. So that's the summary. So far, it's a very, I mean, it's a relatively intuitive concept. It's the same. There's one game where one player wants to fail it, another player wants to succeed it. So theoretically, when D and G reaches Nash equilibrium, so as I said, if you're familiar with the game theory, you probably have a better understanding than I do. I don't know much about game theory, so but we can think of this as a step-by-step process. So first of all, what happens here is Z is some random distribution. It's like N or U, and I think this is U here because the samples are sampled uniformly on this line. So maybe Z is like uniform distribution here. And the black dot here is a true distribution. It's a true PX. And the green line here is what currently Z is at. It's a GZ. So maybe I can, this is PX, this is this is GZ. And this blue line, this blue dot here, the blue dotted line here, is the decision boundary between the two. And what you do first is you first train D. You train D when you go here. Then you see that the decision boundary is much nicer than before, right? So since the black dot is PX and the green line is GZ, then around here, there's nothing, no support in GZ, and then there's like some things are here like for the PX. So you can see that the decision boundary here, this is 1, but starting from here to maybe here, when these two sections intersect, that is when, so like right here, that is when the decision boundary or the discriminator starts to get confused. So you can see that it is decreasing from 1 to 0 gradually, and then when these two meet here, the GZ and PX, when they meet here, that is when the decision boundary, the prediction score is 0.5, right? And then after that, when PX's support is gone and all that's left with is GZ, then this is when the output of the D function is 0. So you can see what's happening here. So once we have this well-informed decision boundary, or when the training of D is finished, then it's time for training of G to begin. So this is when you train G. Keep trying to write Q here. Train G. So what does G want to do? G wants to fool D, right? But since we already know the decision boundary of D, then all we need to do is slightly move GZ to the left, right? Like a little bit here. So that now the D's accuracy, or the D cannot anymore successfully like maximize the cross entropy, or it fails most of the time in terms of distinguishing between the real and the fake samples, because now G is a little bit closer to PX. So then what happens is then we need to retrain D so that there's like a better decision boundary like this. And then we start keep doing this over and over again. Train D and then train G and train D and train G and over again. And then sooner or later, in the end, we will have a perfectly shaped GZ. We'll have a GZ that perfectly approximates PX. And obviously, nowhere in this entire space, D will be able to distinguish between real and fake, because now GZ is exactly the same as PX. So all D can do is always spitting out 0.5. It's always 0.5. So this is when Nash equilibrium is reached. So theoretically, when we're playing a two-person min-max game, when we reach a Nash equilibrium, then these accuracy will be 0.5 all the time, and G will be the same as PX. Will be the same as G. So this is guaranteed. Like theoretically, this is guaranteed when Nash equilibrium is reached. But in reality, we never know that we will reach Nash equilibrium. And this is not. And if you go to, several slides later, we'll actually see that this is no longer a min-max game. This is going to be a max-max game. So this is all just theory, but it's a beautiful theory nonetheless. All right, so moving on. Oh yeah, not several slides later. Next slide, directly next slide. So modified min-max game. So in practice with this game between the two, with this game, especially for G, it doesn't train very well in practice. In practice, G doesn't learn very well. So G trying to fool D was this guy, right? This is the cross entropy without the first term, because first term didn't have anything to do with theta G, so we threw it out, right? So this is cross entropy with only the second term. So in the initial phase, when you start training GAN model in the initial phase, D easily overpowers G, because the job of D is way easier than G, because G needs to generate fake samples, but D only needs to look at two samples, fake and real. And all it needs to do is decide which one's real and which one's fake. And in the initial phase, G will be generating really weird samples, like black samples or white samples or blurry samples or gray samples, completely unrealistic samples. So it will be very, very easy for D to distinguish between real and fake, right? So the initial phase, D easily dominates G. So when you look at it, D. So that means that DGZ will almost always be 0. Because GZ, so this is the fake sample, this is X prime. So DX prime, D will easily say that DX prime is 0 and DX is 1 in the initial phase, when generator is bad at generating realistic samples. So when DGZ is always almost 0 in the initial phase, what happens is this will become 1 minus 0, and that becomes log 1 minus 0. That means that log 1, which means that it'll be 0, basically. Like this term will be 0. So when this term becomes 0, then the gradient will also be 0 mostly. So actually, if you look at this, is a bit more intuitive. So here, this is the graph of this term. Sorry, that was right. So this graph here is the graph of this term here. You can actually see there's one here, like this guy, and the x-axis is DGZ. So we just said that in the initial phase, DGZ will almost always be 0. So almost always be 0. So when you look at 0, it is like around here. So in the initial phase, your DGZ will only oscillate between like some region, like very small region in the initial phase, like 0. So that it'll be mostly living around here. And you can see that the gradient of this region is usually 0, like very, very small gradient. We want large gradient, like this here. Like we want large gradients to, rapidly update the parameters, but unfortunately, with this formula here, we'll have a log function look like this, and then initial phase will be only playing around this field, and this field, the gradient will be 0. So that is why G doesn't learn very well in the initial phase. So what we do is we actually modify the G objective. Instead of trying to minimize this term, we now try to maximize this term. So there's no longer 1 minus here. So 1 minus is gone now. So, and you can see that this is max, not min. So if you look at this term here, log dgz, then it'll have a function that looks like this. And when dgz is 0, in the initial phase is almost 0, right? So we'll be playing around here. And I don't know why they put it negative. Maybe it's because we want to minimize this. I'm not sure. But and you can get the gist. Like if this is a log function that will be playing around here, that means that your gradient will be pretty high, pretty like strong compared to playing around here. So in the initial phase, when dgz is 0, the gradient will be actually stronger now. And that is why we use a modified G objective. So now you can see this is it's no longer a min-max. It's no longer a min-max game. Oh, where did min? Yeah, it's no longer a min-max game here, where max was for theta d, min was for theta g, but now we're playing max g. So it's a max game, and it's no longer min-max game. That there's no Nash equilibrium, and they all just the theory is kind of lost here now. But still, it works pretty well. It works way better than this guy. So probably doesn't matter. Like no Nash equilibrium, but probably doesn't matter. As long as we get good images, good synthetic images, that's all we want. Right, so that's it. So training GAN typically goes through this algorithm here. So for certain number of predetermined number of iterations, we train, and you can see the K steps here. What K steps does is that for K steps, we update theta d. And for after the K step, we update theta g. So it's a bit of an unfair process. We update theta d, we update discriminator K number of times, and then we update generator only once. And then we go back to, again, updating D several times, updating G, updating D several times, updating G, and we keep repeating the process until we are satisfied. So why is that? So why do we update K? Why do we update discriminator a bit more, like several times more than updating G? And yeah, sure. Yeah, that was good answer. 일단 D를 좋게 만드는 거 우선하기 위해서입니다. Right. So if D is kind of like a teacher. D is the police. So we need a good teacher so that G can learn good signal. If D is a poor teacher, D cannot learn a good signal because I'm sorry. If D is a poor teacher, G cannot learn a good signal because G's signal depends on D actually. So D needs to be a good teacher so as to like propagate a good signal back to G, and then so that G can start generating realistic samples. So, but this is kind of like a hyperparameter. Like there's no good value for K that works all the time. Like K equals 5, K equals 10, K equals 1, 2, 3. Like doesn't really, like there's no great way to determine which one's a good number. It all depends on what kind of task you're doing. I mean, what kind of data set you're using, how large like the model how large your model is, whatnot. Like you just need to try out all different Ks and see which one works the best for you. Right, you're right. Like 현섭님 그 아주 맞는 말입니다. 근데 실제로는 이제 D가 또 너무 G를 오버파워를 하면은 막 D가 이제 D는 막 액큐러시가 99.99, 뭐 G는 거의 못한다 이러면 이제 G가 또 아예 배울 기회가 또 아예 없어버릴 수도 있거든요. 그래서 그러니까 이게 이제 뭐예요? 뭐 강아지랑 놀아줄 때도 이제 강아지랑 그 줄다리기 할 때도 약간 놔줬다가 또 땡기다가 뭐 이렇게 하고 뭐 이제 부모님이 애들 가르칠 때도 일부러 져주기도 하고 뭐 이기기도 하고 그러잖아요. 그러니까 이제 약간 이게 밀당을 해줘야지 학습이 잘 되는데 그냥 무조건 그냥 찍어 누르면은 D가 또 G를 그러면 이제 학습이 또 잘 안 될 수가 있거든요. 그래서 요 K가 어느 밸류가 좋냐라는 거는 사실 뭐 미리 알기가 힘듭니다. 학습을 하면서 로스 펑션이 떨어지는 걸 보면서 이제 G가 이제 제너레이트 하는 이미지를 보면서 이제 D를 좀 조절을 해주고 뭐 이런 트릭들을 써야 돼서 그래서 이제 괜히 학습이 좀 쉽지가 않다. 괜히 학습이 굉장히 unstable하다라는 걸 알 수가 있습니다. So as I was just saying in Korean, you don't want D to completely over-dominate G. You need to give some opportunity for G to learn something, right? Just like how you play with your dog like a tug of war. You let it win sometimes and you win sometimes. You know, even though you can win all the time, you let it win. You let your dog win a couple of times so that it just, you know, like feels a success, right? So just kind of like that. Like you need G to do something so that you don't want like a super like strong D. So you need to watch. I mean, this is all back in like 2014, 15, before you had like a lot of great tools to see how the training goes. But before, in 2014, 2015, you had to actually look at how G and D like trains by looking at the loss functions and then sometimes generating the synthetic samples and see where it goes. So you need to monitor the training situation and tune the hyperparameters accordingly. Right, so if you look at case steps, within each case step, you sample some M noise samples. So this will be the uniform distribution or normal distribution, whatever. I mean, this. So you sample like a bunch of Z's, and you sample a bunch of M's. I'm sorry, bunch of X's. And then what you do is you plug these Z's into the generator, so you get a bunch of X primes. And then you plug these into X, you plug these real samples X to the discriminator. And then you just simply try to maximize this term. And after you've trained your D, then you just sample Z from this random distribution, plug that into here, the generator, and then you try to maximize this term. So that's it. So the training procedure is, I mean, the whole algorithm is pretty much like very, very intuitive, very simple. It's just that the training itself is often very unstable because you can see that they're trying to win over each other. Right, so yeah, what's the best value of K? We don't know. We just need to try them out. So when to stop training? So we are, as I said, there's like for a number of training iterations. So it's like there's like a predetermined number of iterations that you need to reach. But in reality, you don't really know. There is no golden rule when to stop training. You just need to, because D and G oscillate, because D wins and G wins and D wins and G wins. Like they need to like take turns and then try to dominate the other person. So because D and G oscillate, we never reach Nash equilibrium. I mean, there is no Nash equilibrium anyway, because we're playing a max game now. So there's no Nash equilibrium anyway. So typically what we do is we generate fake samples from time to time. So like every 10 iterations or every 100 iterations, we generate fake samples, like, you know, by giving the generator the Z, and then see if we are satisfied with the generated samples, the synthetic samples. So it's like people actually looking at synthetic samples and then determining this is like good enough, or we need to further train. Like it's just human eval. So yeah, if there's no visual improvement, then stop training. Or we can use an evaluation metric called FID score, which we'll be talking about in a moment. So because, as I said in the beginning of GAN does not have an explicit parametric function that approximates the likelihood of the samples, unlike VAE or unlike autoregressive model, where there is a parametric function to calculate likelihood. In GAN, there is no way to directly calculate the likelihood of your generated samples, the X primes. So it is a problem, because if you were playing with autoregressive models or VAs, you can like calculate the likelihood, and if you're satisfied with the likelihood, then you can stop the training, right? But in GAN, there is no likelihood function or whatsoever. So all you can do is just look at the samples with your own eyes and then see if you're satisfied, and then stop training, or use a indirect evaluation metric called FID score, and then see if you're satisfied with the FID score. And when stop training. So there were a lot of GAN variants in like 2014, 15, 16, 17, like a lot of GAN variants to stabilize the training process and try to give you a better understanding of what's going on, give you a better indication, like better number, so as to you can look at that number and see if you're satisfied with the training process, something like that. So for example, there's something called Wasserstein GAN, which gives you a more indicative G loss. Instead of like looking at this G loss, if you look at Wasserstein GAN G loss, it's a bit more intuitive. Question from 동원님, G와 D의 액티베이션 펑션을 여러 경우의 수로 상이하게 설정하면 좀 더 완전 좋은. 그렇죠. 네, G랑 D가 사실 이제 제가 G랑 D를 어떻게 셋업하냐 아무 얘기를 안 드렸는데, 사실 G랑 D는 무엇이든 할 수 있습니다. G가 MLP가 될 수도 있고 RNA 될 수도 있고 트랜스포머가 될 수도 있고 CNN 될 수도 있고 뭐가 되든 상관없고 D도 마찬가지입니다. 그래서 G랑 D 아키텍처 뭘로 설정하느냐도 굉장히 트레이닝의 스테빌리티에 영향을 많이 미치겠죠, 당연히. 그래서 좋은 질문이십니다. 그러니까 액티베이션뿐만 아니라 무슨 아키텍처 쓰냐 자체를 아직 한 번도 우리가 얘기하지 않았어요. 굉장히 추상적으로 얘기하고 있죠, 지금. So the question was, like, does the activation function in either D or G like matter in terms of like stability of the training process? And the answer is obviously yes. And if you have been following along, you will have realized that I have never even talked about what kind of architecture to use for DNG. I didn't talk about any like let's use CNN or let's use transformer for DNG. I didn't say anything about that. So it's all abstract ideas right now. And in this Thursday, the practice session, you will be using just simple multi-layer perceptron for generating MNIST images. So we haven't even learned CNN yet, right? So we can't use CNN in this practice session. So we'll first try out GAN with MLP, and then next week we'll learn CNN. Question from Cedric. If I understood correctly, in a max game, as there is an equilibrium, we will just want to train our model until they plateau. We call it right, exactly. We call it as the min-max game has an actual clue of when the model is in equilibrium. Do we know when it has? I'll get to that later. When the model is in equilibrium, can we switch back to a min? As the min-max game has an actual clue of when the model is in equilibrium, can we switch back to a min-max game training once both? That means like when we start with max, can we switch back to min-max? That's a good idea. I'm not sure if anybody has tried that, but I'm going to assume that the end result is not so much different, because even if you play in min-max game, you cannot reach Nash equilibrium anyway. I mean, no, that's a strong statement. We have no guarantee that we will reach Nash equilibrium ever, even if we play a min-max game. So that is because the true min-max game, if I remember correctly, I studied this like way long time ago. So this is just from borrowing like knowledge from like 9 or 10 years ago. This min-max game needs to happen at the same time. Like these, the D and G needs to update exactly at the same time to play a true min-max game. But here, we're actually not playing true min-max game. We're training D and then G and then D and then G. We're playing an alternate game, alternating game. So this is not a true min-max game. So there is no guarantee that we'll reach a Nash equilibrium. We will only reach Nash. We're only guaranteed to reach Nash equilibrium when we're playing a true min-max game. But even though the objective function is formulated as a min-max game, the way we train theta G and theta D is not a true min-max game, because we're alternatingly training them one at a time. So there's no guarantee that we'll reach Nash equilibrium even with this setup. So why bother? Hopefully, does that answer your question? Right, it could be a good quantitative matrix. Before I answer Zamalidin, before I answer your question, so there is also a good, so theoretically, when we reach Nash equilibrium, the accuracy of the D of discriminator will be 0.5. So that could be a good indication. Like every single time you train, you update theta D and theta G, like every single time you do this, you can print out the accuracy of D. And when it is like oscillating between 0.48 and 0.52 or whatever, then you can assume that, okay, so since accuracy is almost 0.5, maybe I've reached the equilibrium. That is one way to do it. And I've used that trick like a couple times, but that doesn't always give you that doesn't guarantee that you have reached Nash equilibrium, because that means that maybe D is underperforming. Like maybe D hasn't reached its true potential. Like D is underfitting, for example. Like you remember overfitting, underfitting, right? So maybe D is underfitting, and that is why it's not able to distinguish between real and fake, because that could also happen. If D is a perfect discriminator and it reaches accuracy of 0.5, then we might have reached Nash equilibrium. But D is not always a perfect discriminator because G could also over-dominate D. So it's very tricky to see when Nash equilibrium is reached just by looking at the loss function, the loss value, or the D's accuracy. It's very, very hard to see, hard to know. So in the end, you just look at the images, the fake images, with your own eyes, and then just, if you're satisfied, you stop training. Good, okay. And back to Zamaladin's question. Is there a way to train both D and G at the same time? I'm not sure how to do that. I'm not sure if you can do that with like gradient descent, or can you do that? You okay, I guess you can try something like you backpropagate. So there's a function. This is the function, right? So we're going to call this, there's a function here. You do this with theta, theta, theta D, and there's also theta G, theta G, and so you'll get the gradients, and then maybe you can update. Yeah, I don't think you can do that. Because you're going to have to update D at the same time. Like for theta G, it only updates this, but for theta, no, sorry. So when you're updating theta G, your theta D will have an effect. So, I'm not sure if you can update both at the same time, if it's possible. But then again, I'm not really sure what it means that like they need to learn at like the two players need to update their behavior at the same time. Like I'm not sure what that really means. I'm not a like expert in game theory. So, like two players updating their behavior at the same time. Not really sure what that really means. If anybody's like an expert in game theory or min-max game, they can elaborate. So when I said that the true min-max game, they need to update at the same time, that is borrowing from my memory. So you like don't trust it like 100%. So yeah, as to your questions, Zamaladin, I guess there's no like good answer. Sorry about that. Question from Lee-Do-hyun-nim. Do we really need to learn G and D from scratch? Is there a way to transfer learn from other models? Loading the parameter of trained VAE generator into the GAN generator. You can do that. That's an interesting idea. Well, what happens if you start with a VAE's decoder? Yeah, if you start with the VAE's decoder, then your G will be pretty strong. But D will soon, I mean, if you, we'll get to the comparison between VAE, GAN, and autoregressive models. VAE's output are not super real. It's like it looks like a image, but it's not as real. It's not like super realistic. So D will easily be able to figure out which one's real and which one's fake. So I'm assuming that VAE decoder's property will be lost very soon. Well, just a preview. Like VAE samples look like this. GAN sample look like this. And clearly the two are different. Because VA is based on reconstruction loss. It's based because VA, if you remember, it's a reconstruction loss plus the KL divergence regularization term. So reconstruction loss is an MSE, it's a mean squared error. So that is why it gives you like a blurry image that tries to, like hit the middle all the time, basically. It hit the average all the time. So it gives you very like blurry, averaged out image. as opposed to GAN, which is super sharp. So this is what GAN can do with the help of a discriminator. So if you start with if you start with the VAE's decoder, I think it'll lose its property and then just transition to this phase. So probably doesn't. Maybe it'll stabilize the training a little bit, but I think in the end, I think the end result will be the same as training from scratch. But yeah, this is all kind of like conjecture, but all good point. Yeah, all good point. Right, so we talked about when to stop training. So I guess this was enough. And then generating fake samples. How do we generate fake samples? I guess this will be very easy. You just how do we generate fake? We just sample from U and whatever we just sample Z from some random distribution. Z from the random distribution. Actually Z from random distribution and 0 Y, and then we plug that Z into G, and then that goes like this, and then this becomes our X prime, and that's it. There's no like, if you think if you're familiar with diffusion, or if you've ever used like Stable Diffusion's demo website, it takes a long time to generate fake samples. Like, it takes like 8 seconds or sometimes 10 seconds, 15 seconds, based on how many users are using Stable Diffusion. Anyway, but in GAN, all you need to do is sample, generate, take one Z out of N or U for that matter, plug that in, and then that is your fake sample, and that's it. So it's super fast, but it's not that different from VAE actually, because after you've trained VAE, the way the method that you use, the method you generate fake sample is just, again, like sample from N and then plug that into the decoder, and then that is your synthetic image, right? So it's not so different from VAE. One thing we need to look at very closely is something called mode collapse, which still like, harasses GAN to this day. Like, GAN has not completely overcome this issue even after 9 years. So what is mode collapse? It's what if G generates just one realistic fake sample, like just one. Like, if you remember my analogy about the whole space between, whole being like all the dog images here, all the cat images here, all the people images here, and then you have a like a distribution, 3D some 3D density function, something like this, and then what you would like for G to do is to approximate this density function, probability density function of X or Px as exactly or as accurately as possible. But G actually doesn't need to do that, because as long as G fools D, G doesn't need to care about the diversity of images. As long as it can fool D all the time with one specific example in your entire space, it just needs to pick one sample and then use that sample to fool D all the time, then its mission is accomplished. So it is very, very appealing for G to fixate on one realistic sample and just forget about the diversity. Like, after you've trained GAN and then you start sampling. So do we have? Okay, we don't have that. If you remember, actually, we can go back all the way back right here. So what we would like G to do is to become like this. But what G can do instead is actually a point estimate like this. And all your Z will be going to one place all the time. All your Z will be going to that place. So G is like it becomes collapsed basically, because we want G to spread the Z. We want Z is a normal distribution, uniform distribution, right? We want G to spread Z as uniformly, or as as like diverse as possible, so as to cover the true PX, right? But instead, what G can do is G can convert Z into one place, this particular one place, which is realistic enough to fool the discriminator. So this can easily happen. So that is, when that happens, we call that mode collapse. So yeah, when G generates sample of limited diversity, or maybe even like not limited, just one sample, like one same person with a very, very minuscule difference between different samples, like maybe like one pixel difference. So yeah, so this means that G is trapped in the local minima. And yeah, this can easily happen because, as I said, training process of GAN is extremely unstable. So that is why G can easily fall into mode collapse. And there was a lot of work that tried to handle mode collapse one way or the other. And like you can tune hyperparameters, or you can use something called Vesterstein. This is like old knowledge. I don't think people use these anymore these days. It's either style GAN or something else. Anyway, yeah. So there's still, to this day, hasn't been a fundamental remedy to completely forget about mode collapse. Like it still lurks in GAN training. You can always meet mode collapse at one point. So that is why diffusion is such a much more preferred generative model these days, because it's easier to train. GAN is hard to train. GAN is like very unstable. Diffusion is easy to train. It's relatively way easier than GAN. It's way more stable, and it rarely falls into mode collapse, interestingly. So it's just that super slow compared to GAN. Diffusion is like really slow, like maybe 100 times slower. All right, so that was it. So now we're going to VAE versus autoregressive versus GAN. So I've just shown you this. So VAE, pixel CNN, GAN. So VAE gives you a very blurry image. Pixel CNN gives you a pretty good image. I mean, autoregressive models are very good, like overall. If you think about ChatGPT, like autoregressive models are super good. And GAN gives you the sharpest image. You can like even like pixel CNN, it's a little bit blurry, but it's like very high quality. But GAN is like very sharp. It's kind of like real person. Like the strands of hair, like the hair, you can see the texture here. There is no strand of hair here. Like they're all mushed, right? But here you can see the strands of hair. So GAN is like very weird in that sense. It's very realistic, very sharp. So yeah, VAE image quality very blurry due to the squared error loss, and modern VAE generate better image. This is old news. Like as I said, diffusion can be seen as a sequence of VAE, so you better use diffusion if you want the image quality. Pixel CNN, it gives you a pretty good performance. If you like, it gives you overall like pretty good image quality. It's just that it's slow. And DALL-E 1 and I think it was Google's Party, Google's PARTI, Party, was using the same mechanic, using autoregressive model with the visual codes instead of visual pixels. Gives you a pretty good performance. But I think diffusion is way more preferred. And GAN, so sample from, it's sharpest quality, both collapse alerts. And the measuring performance, this is still an issue. Like for VAE, measuring performance can be seen as a loss. Measuring performance, we can simply use reconstruction loss between X and X prime and see look at the MSE loss. For pixel CNN, we can calculate the likelihood using this. But for, as I said, with GAN, there's no like easy way to directly measure the performance of the model. You can just use your own eyes, or we are going to use something called FID score, which we'll get to in a minute. Right, the sharpest image quality, even like StyleGAN is a pretty recent development. So StyleGAN was able to generate 1024 by 1024 images, really high quality, high resolution images, and that was like a breakthrough in GAN, because people used to play around with like 128, or maybe even 256, but larger, like high quality images was very challenging. But then StyleGAN came up with like a couple of neat tricks to make it happen. So if you're interested in like GAN state of the art, then you should definitely study StyleGAN. There's like StyleGAN 1, StyleGAN version 2. I think there was StyleGAN something called like discriminator trick, something that came out like a couple years ago. I'm not sure what happened after that. But anyway, still gives you a very good image. It's just that hard to train and mode collapse. Right, cutting edge progress, there's obviously diffusion. So if you look at DALL-E 2, I mean, DALL-E 3 came out, and DALL-E 3 is now, if you read DALL-E 3's announcement, it'll reject your request to generate images in a certain designer's style, like because of all the issues with the intellectual property. DALL-E 3 will no longer respect your request to follow like certain designers' art style or generating a real person. Please give me a Robert Downey Jr.'s portrait wearing a funny hat. It will not do that anymore. DALL-E 3 will not respect your request to generate real person. It'll just give you like fake images for fake purposes. So not fake purposes, for let's say artistic purposes, or like unharmful, like provocative purposes. So if you're interested in generating real person, you should definitely try out stable diffusion or Midjourney or something else. Anyway, so this can be like, this is a very, very high. I mean, if you zoom in, you can see the strands of the horsehair, right? So very high quality image. With modern architecture, modern diffusion, you can do things like completely weird stuff, like astronaut riding a horse in a photorealistic style. This is, yeah, phenomenal quality. This is party. Okay, so this party. This is the auto-regressive model with something called visual code. I haven't talked about what visual code is. We'll just skip that in the interest of time. So a map of United States made out of sushi. It is on table next to a glass of red wine. So it all respects the image, completely respects the requested text. United States map made out of sushi, and then there's a wooden table, and then there's like glass of wine here, so it's all there. And sometimes DALL-E 2 wouldn't be able to do that, so that was the selling point of Party. Like Party said, like, our model respects your request as detailed, as loyally as like high fidelity. And sometimes Stable Diffusion or DALL-E 2, they would not be able to understand your request. So that is why people try to come up with like prompt engineering, like weird like weird like words or tokens to generate like generate high quality images with Stable Diffusion. So DALL-E 3, they claim that you don't need to do that anymore. You just need to write a very detailed text description and it'll completely be loyal to your request. But you can't generate. But your freedom is very much limited. All right, so we'll get to diffusion later. So hang tight. Evaluation. So this is the last one. Actually, no, there's one more, but we'll skip this. We'll actually we'll pick up our pace here. So evaluating GAN. There was no, as I said, there was a direct way to evaluate how good image quality is. So we cannot use likelihood function. We cannot use reconstruction, just like VAE, Pixel CNN, because they are explicit models. But GAN is an implicit model. It doesn't actually care about giving you an explicit parametric function of your true density. So difficult to measure the quality of examples. So there are two popular metrics. One is inception score, IS, and another is called Frechet inception distance score, FID. So inception score is no longer popular, widely used, but FID score is still very relevant. So maybe you should keep this in mind. Like, you will see FID score in a lot of generative model papers, even to this day. We'll start with the inception score. So what is an inception score? Inception score comes from a model called Inception version 3. So we'll get to CNN next week. So until then, you don't need to care about the details of this model. But Inception model is basically just a ImageNet model. It was trained on ImageNet training samples. So it can, when given a certain image, it could be any arbitrary resolution. When given an image, it'll classify that image into one of the 1,000 classes, the ImageNet classes. So it's like very granular, like image, like camel, zebra, elephant, and like bears, like different bears, like grizzly bear, like black bear, brown bear, like all kinds of classes. So model architecture looks like it's a pretty big model. And at the end here, this is where you get 1,000 logits, basically. So that's inception model. With the inception model version 3, so there's version 1, version 2, version 3, and we'll get to that later. With inception pre-trained version 3, what we want to do with this classifier is we want to evaluate based on two criteria. So image quality and image diversity. So when you have a GAN model and you generate a bunch of fake samples, we want to take those samples and then put them through inception version 3 and then evaluate the quality of individual image and the diversity of overall images. So how do we do that? So for image quality, a single image should have a focused py given x, which means that you're out of 1,000 multinomial distribution, out of 1,000 classes. This is like cat, dog, bear, elephant, camel, whatever, like all that. You want your image to have one particular spike in one class and very small, very low probability in all the other classes. So this is like high quality image, or at least that's what they thought. The authors of Inception score, that's what they thought. So for a single image, you want py given x to have a very low entropy. So high entropy is when everything is uncertain. Like every class has like some amount of non-zero probability. So that's high entropy. Low entropy is when one class dominates completely and all the other class have like near zero probability, right? So we want py given x to have a low entropy. And when it comes to image diversity, we want all py, marginal probability, py, over all images should not focus on one class. So as for py, the marginal probability, we want it to be non-zero everywhere. So high entropy in this case. So for a single image, low entropy. For all images, high entropy. So that's the objective that we want to achieve when it comes to training GAN. So we calculate the relative entropy between the two because we want this to be low, we want this to be high. So we calculate the relative entropy between the two, and actually KL divergence is the relative entropy between the two. So we calculate the KL divergence between the two, and obviously you want it to be as high as possible because we want this and this to be as apart. Like we want this to be low, we want this to be low, we want this to be high, so we want KL to be high, right? So yeah, for specific algorithm, we actually there's like specific algorithm all the way here. So if you're interested, you can look them up. So that was inception score, and for worst inception score you can get is 1.0. So 1.0 is the worst you can get, and the best score you can get is n, which is the number of output classes. So if you're using Inception version 3, which is 1,000 classes, the best score is 1,000. So there's a good, nice, intuitive example here. So if you are doing a three-way classifier, so 3 classes, there are only 3 classes, 1, 2, 3, then if your probability output of 3 images, image 1, image 2, image 3, looks like this, so one in different classes, then this will give you inception score of 3, the perfect score, because there are n equals 3, because there are 3 classes, right? So this, you can see that for this guy, low entropy, but when you marginalize it, then you'll get 0.33, 0.33, 0.33, right? So this is high entropy. So that is when you get IS of 3.0. If you get this example here, then this is the worst possible case. Like low and high entropy individually, and this just leads to the worst inception score possible. So that's the inception score. And now we go to FID. So inception score is based on the output of your inception model, the 1,000 classes, right? So that was inception score. FID is not based on the output. It's actually using a penultimate layer here. So this is when you get 1,000 logits, but here it's right before that. So before, this is a 2048 dimensional vector, 2048. So if your input image was 128 by 128 by 3, then that is all collapsed into this 2048 dimensional vector. So you take this vector. So this is probably like, it has all the information you need in order for your 1,000 classifier to work good, right? So it captures a lot of like good semantics. So you take this and then you compare the distribution of features between real and fake. So that means that you put a lot of reals, a lot of x1, x2, x3s into this, and then you get a bunch of, I'm going to call this z. So you get z1, z2s, z3s. You do that, and for x primes, the fake one, you have x1 prime, x2 prime, x3 prime, the fake ones, and then you put this in, and then you'll get z prime 1, z prime 2, and z prime 3, right? Prime 3, right? So you have a bunch of z's between real and fake. And what you do is you calculate, and you assume that zi's will follow is following like normal distribution. Z prime i's are also following normal distribution, and you calculate the distance between two normal distributions. So that's what this FID score is doing. So when you calculate, and I said that you calculate the distance between two Gaussian distributions, and you use something called Frechet distance to calculate the distance between the two. So this Frechet distance is also called faster sine 2 distance, if you're familiar with this kind of stuff. So we don't use KL, we don't use none of that. We use Frechet distance to calculate the two Gaussian distributions, where one is a real, so the z's, and the other is z primes. Right, so we're no longer using the direct output of 1000 class. We're using the distribution. And the another important thing is when calculating inception score, all you needed was fake samples. You only needed fake samples to push it through inception score and then get the output probabilities. And based on that, you were calculating inception score. But here in FID, you need two. You need real and fake, so as to get the real distribution, fake distribution, and then calculate the distance between the two using the Frechet distance. So it's a little bit more work, but it gives you a bit more like intuitive, or more like, you know, qualitatively satisfying result. So okay, calculate the calculating the distance between two Gaussians using Frechet distance. It follows this nice formula equation. And if you're interested, you can look at the algorithm in the way back in the final page. So this is M from the real, covariance matrix from the real, M from the fake, covariance matrix from the fake, and yeah, that's it. So you're basically calculating the Gaussian distance in the 2048 dimensional space, because we're using this guy. Right. So the good thing about FID score is that it actually, you know, like corresponds well to your visual intuition, basically. So if you start adding noise, like Gaussian noise, disturbance level, like disturbance like 0, 1, 2, 3, FID score increases. FID is distance, so you want as low FID as possible, right? And same with the blurriness, same with the salt and pepper, same with like, what is this? It's like distortion. So as you increase the disturbance level, FID score will always increase. It is all increasing. So that's the strong preferred property of FID, because it kind of correlates well with your visual perception. Right, so that's FID score. And finally, yeah, applications of GAN. There was text to image, some like very old examples that use GAN for different purposes. One is obviously we wanted to generate images based on text descriptions. So the very first one was proposed by Scott Reed in 2016. So it's a conditional image generation using text input. So I think the text input was based on the RNN text input. So you put some text like this into your RNN, and then you take the hidden layer of your RNN and then push that into, and use that into generating, you know, into the generator and the discriminator of GAN. So that was, yeah, I mean, as opposed to today's standard where you have DALI 3 stable diffusion, this is very, very like basic. But this is like 7 years ago. But it was back then it was a pretty like interesting discovery. Like you can generate images with text description. That was a pretty like impressive achievement. And CycleGAN is another like big thing that's still used today. So the concept of GAN and CycleGAN, all this is like used in a lot of different places, not just for image generation, but like the idea of GAN is that you can have a discriminator to satisfy some condition without considering the explicit parametric function of the underlying distribution. That's the beauty of GAN, right? That like we no longer care about how it works in the underlying distribution. We just want the output. We just want the result, and that's it. So that's the beauty of GAN. And that kind of like philosophy is used in a lot of different places in deep learning, not just for GAN, but like training and tuning your models. CycleGAN is the same. It has a very interesting setup. So there's like, it's a style transfer. And obviously there's adversarial loss, the adversarial loss meaning the GAN loss, but there's also cycle consistency. So you have like zebra and you want it to be like brown horses. So what you do is you have a generator that takes the zebra image and then generates the whatever brown horse it wants it, and then there's a backdoor that goes back to the zebra, and this you want this backdoor to give you the original zebra. Still, like there's like consistency loss. So there's like cycle consistencies. I mean, there's not enough time to talk about cycle GAN, but if you're interested in style transfer, or cycle GAN or like this kind of stuff, you should definitely take a look at read the papers, the cycle GAN and all the derivatives. Right, and the last one is style GAN. So style GAN is the very first, I think it is probably the first model to generate extremely high quality, high resolution images. I think it comes from NVIDIA, Keras, and high resolution samples using various techniques. Like, there was a lot of technique. Instead of putting Z directly into G, it actually massages Z through some multi-layer perception, like multiple layers of NLP. So you manipulate the Z so it looks nice enough to feed into G, and then there's like ADA-in, which is adaptive instance normalization. So like this also is like a strong contribution coming from like GAN, like style GAN and all that. And bilinear upsampling, layer noise, there's a lot of different techniques to make this kind of image happen. So this is like extremely high quality, right? The strands of hair, like the texture of this hat. I'm not sure if this is a hat, and like the wrinkles here, and and obviously this is not a real person. This is just fake person that was hallucinated by style GAN. So it's some composition of people that style GAN has seen from the internet, right? But it is like if you show it to some person who doesn't know anything about GAN, then they will definitely believe that this is a real person, right? But so yeah, so the battle between GAN and diffusion, I think it's not completely over unless diffusion finds a way to speed things up. It'll get there sooner or later, but still, I think some people still try to conduct research on GAN to make it overcome the mode collapse and all that. So we'll see. All right, I think this is it. So we are 2 minutes over. So considering I've wasted 5 minutes in the beginning for the iPad thing, I think this is a good ending. Question: when comparing performance between models in GAN, does low FID necessarily lead to visibly better performance, or would a human visual review process also be necessary? If you're generating general domain images like birds or cats or dogs, I think FID score is pretty much reliable because it has been tested so many times over like like so many years. So I think in general domain, FID score is pretty much reliable. Like if you reach FID of like 7.65, it's like indistinguishable by human eyes. But if you're generating like X-rays or some pathologies, like very domain specific, non-general domain images, then there's no like FID is not super reliable. So in that case, you definitely need expert human assessment. Great, yeah. Any other question? 앞에서 DKL, QPL 차이점. 그러니까 이제 DKL, QP는랑 DKL, P, Q가 있을 때 이게 이제 베리에이셔널 베이스고 이게 이제 expectation propagation이라고 했는데 사실 요거를 보면은 Q 로그 Q P고 요거는 P 로그 P Q잖아요. 근데 여기 이게 지금 이제 우리는 보통 DK를 낮추고 싶잖아요. 지금 둘 사이의 간격을 좁히고 싶으니까 DK를 낮추고 싶잖아요. 근데 언제 그럼 DKL이 높아지고 낮아지냐를 보면은 얘를 보면은 P가 위에 있고 Q가 아래에 있잖아요. 그러니까 이제 예를 들어서 P가 만약에 넌제로인 그러니까 서포트가 있다. 어느 부분에 이렇게 서포트라는 게 이제 여기까지 서포트가 있는 건데 여기 이제 P가 제로잖아요. 그러니까 그런 걸 얘기하는 건데 지우고 이제 그러니까 P가 넌제로인데 예를 들어서 Q가 만약에 0이다. Q가 없다. 그러면 어떻게 되겠어요? 얘가 지금 그냥 폭발할 거 아니에요. 지금 엄청 올라갈 거잖아요. 거의 무한대로 올라갈 거잖아요. 그러면은 DKL이 커지잖아요. 그러니까 그러면 안 되니까 요런 걸 쓸 때는 P가 0 이상이면 Q도 0 이상이어야지 얘가 낮아지잖아요. 그렇기 때문에 아까 그 그림에서 P가 만약에 P가 이렇게 생겼으면은 Q는 이걸 다 덮어야 되는 거예요. 이렇게. 왜냐면은 P가 제로가 아니면 Q도 제로가 아니어야지 KL이 낮아지기 때문에. 요게 낮아지기 때문에. 근데 반대로 얘를 보시면은 QP를 보시면 Q가 위에 있고 P가 아래에 있기 때문에 P가 0인 P가 0이 0인데 P가 0인데 Q가 0이 아니면 큰일 나거든요. P가 0인데 Q가 0이 아니면 얘가 또 폭발할 거잖아요. 그러니까 반대로 이때는 이렇게 생겨야 돼. 이렇게. 그러니까 P가 0인 곳에서는 Q도 무조건 0이어야지 로그 QP가 폭발하지 않는단 말이에요. 그러니까 두 개의 비헤이비어가 완전 달라진다. 두 개의 비헤이비어가. QP랑 QPQ의 비헤이비어가 완전 달라져서 PQ로 가면은 PQ로 가면 이렇게 널찍하게 P가 커버하는 모든 걸 다 커버하려는 아주 널찍한 가우시안이 나오고 QP로 가면은 P가 없는 곳에는 Q도 없어야 되기 때문에 모두 하나만 커버하는 요런 이제 애가 나오게 요런 가우시안이 나오게 된다라는 얘기입니다. 그래서 얘의 장점은 PQ의 장점은 이제 다 커버하기 때문에 아주 다이버스한 뭔가가 나오겠죠. 그러니까 P가 있는 곳에는 Q도 무조건 있기 때문에 P가 나올 P의 샘플들을 Q는 어쨌든 제너레이션 할 수 있는 능력이 있지만 이제 이런 갭이 생기는 거죠. 이런 갭이. 있지도 않은 곳에서 자꾸 샘플을 한다거나 뭐 이런 데서. 근데 이제 QP의 장점은 Q가 만든 것은 무조건 P 안에 있어요. 그렇기 때문에 Q의 제너레이션은 P의 제너레이션일 거라는 믿음이 있는 거죠. 프리시전이 높은 거죠. 근데 그 대신에 요런 건 절대 제너레이션 못하는 거죠. 여기서 끝나버리니까 Q가. 끝나버리니까 P는 꽤 여러 개가 있음에도 불구하고 Q는 하나의 모드만 이제 커버 이렇게 어프록시메이트 하기 때문에 P의 모든 거를 제너레이션 하지 못한다. 그래서 리콜이 떨어진다라고 보시면 되겠습니다. 네, 좋습니다. Any other question? 아, 그거는 제가 얘기했듯이 저도 잘 모르겠습니다. 왜 QP가 적합한지. 제가 뭐 여러 개 인터넷을 찾아봤는데 궁금해서. 뭐 명확한 답 뭐 근데 뭐 하루 종일 찾은 건 아니고 몇십 분 찾았는데 없어가지고 포기했는데 한번 찾아보시고 알려주시죠. 왜 그러니까 이제 VA가 아니라 베리에이션을 베이스가 QP를 쓰는 거예요. VA는 사실 그냥 어떻게 보면은 오토인코더에 KL 레귤러이제이션 붙인 건데 그게 어쩌다 보니 베리에이셔널 인퍼런스랑 같은 거더라라는 연결점이 있는 거고 베리에이션 인퍼런스 자체는 굉장히 오래된 테크닉이거든요. 뭐 한 뭐 몇십 년인지 몇백 년인지 모르겠죠. 하여튼 굉장히 오래된 테크닉인데 베리에이션의 베이스에서는 QP를 써요. 베리에이션 베이스에서. 그래서 이제 왜 그럼 베리에이션을 베이스에서 QP를 쓰냐? 라고 묻는 질문이 이제 적합한 질문인지 잘 모르겠어요. 왜냐하면은 이거를 베리에이션을 베이스로 부르는지 베리에이션을 베이스 중에 이거랑 이게 있는데 이걸 선택한 건지 제가 잘 모르겠거든요. 역사적으로. 뭐가 맞는지. 근데 이제 뭐 찾아보면은 결국은 뭘 원하냐. 내가 이제 이런 Q를 원하는지 이런 Q를 원하는지에 따라서 내가 QP를 쓸 건지 PQ를 쓸 건지가 정해집니다. 그래서 정답은 없다. 내가 예를 들어서 P가 가우시안일 그러니까 유니모달이다. P가 유니모달일 거라는 가정이 이렇게 꽤 강하게 있으면 사실 이걸 쓰는 게 좋겠죠. 왜냐면 P도 유니모달, Q도 유니모달이니까 얘를 쓰면은 이제 최대한 다양한 걸 커버할 수 있잖아요. 근데 내가 예를 들어서 P가 유니모달이 절대 아니다. P가 막 이렇다 이러면은 이제 뭐 그냥 그럴 때는 이제 얘를 쓰는 게 낫겠죠. 그냥 차라리 딴 거 커버하는 거 포기하고 그냥 하나라도 잘하자라는 식으로 이게 날 수도 있겠죠. Okay, so any other question? 요새 스타일 같은 경우는 여러 가지 프로세스 추가 스텝이 좀 빠른가? 스타일계는 스테이블 디퓨전은 훨씬 빠릅니다. 스테이블 디퓨전이 느린 거죠. 아까 영어로 얘기한 게 스테이블 디퓨전이 느리고, 그러니까 디퓨전이 느린 거고, 걔는 빨라요. 맨 앞으로 가야 될 것 같은데 그 얘기를 하려면. 디퓨전은 이렇게 여러 스텝을 디노이징을 해야 되기 때문에 포룹을 엄청 돌려야 돼요. 포룹을 한 1000번 돌려야지 이제 워낙 만족할 만한 퀄리티가 나오기 때문에 디퓨전이 훨씬 느립니다. 걔는 그냥 Z 뽑아서 G 넣으면 바로 X 프라임 나오잖아요. 그러니까 훨씬 빠르죠. 네, 한 몇백 배, 뭐 몇천 배 빠를 겁니다. 요즘은 이제 디퓨전도 굉장히 뭐 여러 가지 트릭을 많이 써가지고 빠르게 만들었다고 하는데 그래도 여전히 이제 겐이 훨씬 빠릅니다. Right, any other question? All right, I guess not. So thank you for attending again, even during the 추석 season. So if you have any other question, please ask them on Classum, and I'll see you guys next week. 네, 감사합니다. 수고하셨습니다. 감사합니다. 네, 감사합니다. 네, 고생하셨습니다. 수고하셨습니다. Alright, thank you. Bye bye. Bye bye.